Download this code from codegive.com, link in the description below. OK, let's break down episode 175 of Bruce Perens's podcast, likely Algoram opendv, and the associated concepts of opendv, VHF/UHF, and a practical, albeit simplified, code example. This is a complex topic, so we'll cover the core ideas. Keep in mind that implementing a full-fledged opendv system requires specialized hardware, SDRs, codecs, knowledge of radio protocols, and significant software development effort. This tutorial aims to give you a solid understanding and a starting point. Understanding the landscape, episode 175 and Algoram opendv. Unfortunately, I don't have direct access to the content of Bruce Perens's podcast episode 175 unless you provide me with specific transcripts or summaries. Bruce Perens is a well-known figure in the open source world. He likely discussed a system called Algoram opendv, possibly a project or concept he was involved with. The key elements likely discussed are *Algoram*. This part of the name is likely related to a specific algorithm or set of algorithms used in the opendv system. Without more context, it's difficult to specify exactly what the Algoram aspect encompasses. It might be a particular method of voice coding, error correction, modulation, or demodulation tailored for VHF/UHF amateur radio. *opendv, Open Digital Voice. This is the core concept. OpenDV refers to a free and open-source digital voice codec and communication protocol designed primarily for amateur radio use. It aims to provide a digital voice mode that is not encumbered by proprietary patents or restrictions. *VHF/UHF*. Very high frequency, VHF, and ultra high frequency, UHF, are radio frequency bands commonly used in amateur radio. VHF ranges from 30 MHz to 300 MHz, and UHF ranges from 300 MHz to 3 GHz. OpenDV is intended for use within these bands. What is OpenDV and why is it important? OpenDV is designed to provide a royalty-free alternative to proprietary digital voice modes used in amateur radio, such as *D**, developed by the Japan Amateur Radio League, JARL. *DMR, digital mobile radio, a commercial standard, sometimes adapted for amateur use. *YSF, Yaesu System Fusion, a proprietary system from Yaesu. The advantage of OpenDV is that it allows anyone to implement and use the protocol without licensing fees or legal restrictions. This encourages experimentation, innovation, and interoperability within the amateur radio community. Key components of an OpenDV system, and how they relate to VHF/UHF. A typical OpenDV system involves these key components. 1. Audio input * your voice, captured by a microphone. 2. Voice codec, vocoder. This is the heart of OpenDV. It converts your analog voice signal into a digital bit stream. It's crucial to use an open-source voice codec. Example would be an open-source LPC vocoder. 3. Channel coding, error correction. Radio channels, especially VHF/UHF, are noisy. Channel coding adds redundancy to the bit stream, allowing the receiver to correct errors introduced by interference and signal fading. Common techniques include *forward error correction, FEC. Examples include convolutional codes, Reed-Solomon codes, and more modern codes like LDPC, low-density parity check. *interleaving spreading the bits in time to mitigate burst errors. 4. Modulation * converts the digital bit stream into an analog signal suitable for transmission over the radio channel. Common modulation schemes used in VHF/UHF include *FM, frequency modulation simple and robust. *FSK, frequency shift keying represents bits as different frequencies. *PSK, phase shift keying represents bits as different phases. *QPSK, quadrature phase shift keying, a more efficient version of PSK that transmits 2 bits per symbol. 5 radio transceiver *, the device that transmits and receives the radio signal. This typically involves transmitter * takes the modulated signal, amplifies it, and sends it to the antenna. Receiver * takes the signal from the antenna, amplifies it, demodulates it, and passes the data to the decoder. Software-defined radio, SDRs are extremely popular for opendv projects because they provide the flexibility to implement all the processing stages, modulation, demodulation, codec, etc., in software. 6. Demodulation * the reverse of modulation, converting the received analog signal back into a digital bit stream. 7. Channel decoding, error correction removes the redundancy added by the channel encoder to correct errors. 8. Voice decoding, vocoder converts the digital bit stream back into an analog audio signal that can be played through a speaker. 9. Audio output * the reconstructed voice, played through a speaker. Why is VHF/UHF important? Amateur radio bands * VHF/UHF are designated frequency bands for amateur radio use. This allows licensed amateurs to experiment with radio communications. Line of sight propagation * VHF/UHF signals generally travel in a straight line of sight. This makes them suitable for local and regional communications. Relatively simple antennas * VHF/UHF antennas are smaller and easier to construct than antennas for lower frequencies, example HF. Repeater systems * VHF/UHF repeaters are commonly used to extend the range of communications. A simplified code example, Python, pseudocode. This is a simplified example to illustrate the core concepts. It is not a complete, working opendv implementation. It only focuses on a minimal voice encoding/decoding process. A real system would involve much more complex modulation, demodulation, error correction, and hardware interfacing. Explanation of the code *. 1. Encode _voice, audio _frame, *. This function represents a very simplistic voice encoder. In reality, a good voice encoder would use techniques like linear predictive coding, LPC, CELP, code-excited linear prediction, or more modern codecs, like Opus or Codec 2, although these might not be Algoram opendv. This example downsamples the audio, reducing the amount of data. This is a form of lossy compression. 2. Decode _voice, encoded _frame, *. This function is the corresponding decoder. It upsamples the encoded audio. This is a naive way to attempt to restore the original signal. 3. Simulate _transmission, encoded _frame, *. This is a placeholder for the entire radio transmission process. In a real system, this would involve modulation * converting the digital data to an analog signal. Adding noise * simulating the effects of a noisy radio channel. Demodulation * converting the received analog signal back to digital data. Error correction * using techniques to correct errors caused by noise. 4. If __name __equals __main __: the main part of the script generates a synthetic audio signal, a sine wave. You would replace this with audio from a microphone. Asterisk calls the encode_voice, simulate_transmission, and decode_voice functions. Asterisk includes comments suggesting how to play the decoded audio, using a library like Sound Device or Simple Audio, and how to compare the original and decoded signals. Important considerations and next steps asterisk. Asterisk real vocoders asterisk the encode_voice and decode_voice functions in the example are extremely simple. To build a usable opendv system, you need a real voice codec. Investigate open source vocoders like codec 2 a popular open source vocoder designed for amateur radio use. Its relatively low bitrate. SPX an older but still usable open source vocoder. Opus a very modern, high quality open source codec. It might be overkill for opendv, but it's worth considering if bandwidth is not a major constraint. Error correction implement a forward error correction, FEC, code. This is essential for reliable communication over a noisy radio channel. Research read Solomon codes, convolutional codes, or LDPC codes. Python libraries like NumPy and SciPy can be helpful for implementing these codes, but specialized libraries are also available. Modulation/demodulation implement a modulation scheme, example FSK, PSK, QPSK. Libraries like SciPy.signal can be used for basic modulation and demodulation. Software-defined radio, SDR. To actually transmit and receive opendv signals, you'll need an SDR. Popular SDRs include RTL SDR very inexpensive but limited performance. Good for experimentation. Hacker F1 more powerful and versatile. Lime SDR a high performance SDR. Adalm Pluto relatively low cost, and supports full duplex. You'll need to use an SDR library, example PYRTL SDR for RTL SDR, SOAPy SDR for a more general SDR interface, to control the SDR and send/receive data. OpenDV standards/protocols research any existing OpenDV standards or protocols. This will help ensure interoperability with other OpenDV systems. If Algoram OpenDV refers to a specific proposal or implementation, find the documentation for it. Hardware for actual transmission, you'll need appropriate antennas and power amplifiers for the VHF/UHF frequencies you intend to use. A more realistic example, illustrating codec 2 integration. This example shows the general idea of integrating a codec 2 library. You'll need to install the codec 2 library and find Python bindings, wrappers, for it. The example is still illustrative, as Python bindings may not be readily available, and setting them up can be complex. Python. This is pseudocode, requires codec 2 Python bindings, which are not readily available. Import codec 2 hypothetical codec 2 Python bindings. Configuration. Sample_rate equals 8000. Frame_duration equals 0.0220 milliseconds. Frame_size equals int, sample_rate frame_duration. Assuming a codec 2 mode, example 1300 bps. Codec 2 mode equals codec 2.mode 1300 hypothetical. Initialize codec 2, hypothetical. Codec 2 instance equals codec 2.codec 2, codec 2 mode. Def encode voice codec 2, audio frame. Encodes the audio frame using codec 2. Convert audio frame to appropriate format, example int16. audio underscore frame equals, audio underscore frame asterisk 32767, .as type, np.in16. Encode the frame, hypothetical. Encoded underscore frame equals codec2 underscore instance dot encode, audio underscore frame dot to bytes, needs byte array. Return encoded underscore frame. Def decode underscore voice underscore codec2, encoded underscore frame. Decodes the encoded frame using codec2. Decode the frame, hypothetical. Decoded underscore frame underscore bytes equals codec2 underscore instance dot decode, encoded underscore frame. Convert the decoded bytes to an audio frame, np.in16. Decoded underscore frame equals np.from buffer, decoded underscore frame underscore bytes, type equals np.in16. Scale back to the range -1, 1. Decoded underscore frame equals decoded underscore frame dot as type, np.float 32, /32767. Return decoded underscore frame. If underscore underscore name underscore underscore equals underscore underscore main underscore underscore. Generate a synthetic audio signal, replace with actual audio input. Frequency equals 440 Hz. Time equals np.linspace, 0, frame underscore duration, frame underscore size, endpoint equals false. Audio underscore frame equals np.sin, 2 asterisk np.pi asterisk frequency asterisk time. Dash encoding using codec2 dash. Encoded underscore frame equals encode underscore voice underscore codec2, audio underscore frame. This line will cause issues without proper codec2 bindings. Simulated transmission. Received underscore frame equals simulate underscore transmission, encoded underscore frame. Dash decoding using codec2. Decoded underscore frame equals decode underscore voice underscore codec2, received underscore frame. Output dash. Print, codec2 integration example, requires codec2 Python bindings, dot. In summary, building an opendv system is a challenging but rewarding project. Start with the fundamentals, understanding voice codecs, modulation, error correction, and SDRs. Explore existing opendv initiatives and adapt them to your needs. Begin with simple simulations and gradually add complexity. Remember that real-world radio communications are inherently noisy, so robust error correction is critical. The code provided here is a very basic starting point. It should be seen as an illustration of concepts, not a production-ready system. Good luck.